about admissible filtered finite module. As recall, we start with a filtered finite module over K0, let's call it D, then we define the Hodge number over such filtered finite module D to define to be the Hodge number of K filter space. So this is just base change from K0 to K because K0 is contained in K. Okay. Actually, it's the maximum ramified between QP and K. Maximum ramified extension. And then a subobject, d prime of D, is defined to be a K0 vector subspace. Stable under phi and n, and with filtration given by phi I dk prime equals dk prime intersection with phi I of dk. Definition: a filtered finite module D over K is called admissible if K0 dimension less than infinity, Frobenius is bijective, so it has isocrystal structure, and firstly the Hodge number of D equals the Newton number of D. Moreover, for the submodules, D prime in D will require the Hodge number is always less equal than Hodge number of D prime. So the first part of the exercise show that the condition 2 is equivalent to reverse the direction but define it on quotient objects. Hodge number of D double prime is bigger or equal than the Newton number of D double prime for all quotient object D prime of D, which means there is a surjective morphism in that corresponding category. Proof: indeed, there is one-to-one bijection between subobjects and quotient objects. Of any given filtered phi n module D. The correspondence is very easy. Correspondence between subobjects and quotient objects. As follows. So take any subobjects and map it to the quotients. Conversely, you have any quotient objects, which means there is a surjective map from D to have to map it to the kernel. So the key point is that from the additivity we have proved in last exercise of this Harsh number, we have for any D prime subobject of D, TH of D prime plus TH of D quotient D prime equals TH of D. But this TH of D equals the Tn of D by assumptions. This is a constant. And so to say that all the, similarly we have this additivity of Harsh number, to say that Harsh number is always less equal than the Newton number for subobject is the same as saying that Harsh number is always bigger or equal than the Newton number on the quotient objects. That's the proof. Remark. We denote MF admissible K phi n the full subcategory of filtered phi n module over K, consisting of admissible filtered phi n module. It turns out that this MF, this filtered admissible filtered phi n module over K is a abelian category. We will prove that later in another video, I guess. Second part of exercise today. Prove the following proposition. So again, let's take a filtered phi n module. Then we claim that D is admissible if and only if still is admissible. Proof is actually very quickly, just by what we have proved in the last exercise. The Harsh number of D due is minus of the Harsh number of D. Similarly, Harsh number, not Newton number of D due, the minus of the Newton number of D. This is also what we have proved is indeterminate matrix and its inverse. And then again, plus just the additivity of th and tn, it's easily to prove this equivalence.